Now, let's go through Laplacian number 6, I believe. Yeah. So this lesson is talking about the partition. And we have talked about some kind of the notion before, right? For example, we have a social network, and then you have some connection between two person or two vertices, and somehow we find a good place to cut the graph, so that left hand side and right hand side they are more related to themselves, but they are not so interrelated. But there are other kind of application. I'm not going to show that in this class, but it's just an immediate application of this lesson. Okay, so for example, if you have a picture, this is for example JPEG. Okay, and then there is a person inside. We may assume the picture is grayscale. Okay, so there are something like this is outside is pretty much the background is white, and the person, the figure, is gray. So you want to partition the pixels into two parts, so that you can take out the picture, so that you can touch the photo, right? This is quite common today. So what you can do is try to set each pixel as a node, a vertex, and this is also a vertex. So you have lots of vertices outside. And they are connected if their color is similar. And so somehow the human part, it is connected to themselves. I don't know, I'm just drawing something. And somehow it is not so connected to the outside part. So if you can change the picture into a graph and then try to partition the vertices, then you are basically partition the pixels, and the pixels represent a segment on the picture. So you can take the certain part of the picture outside. It is possible that you can cut the picture so that you only take the human part, the main part, and then take it outside. It is doable, and so that's kind of the application of this lesson. So in order to do so, we will utilize the Laplacian matrix and then try to understand some of the optimization problem to see why this works. Okay, so here is a simple question. I call that as Q1. Suppose I have a graph which is on two n vertices. It's just for convenience that we have an even number of vertices. So we want to find a partition of the graph, a partition of the edges, a partition of the vertex set. How to partition V of G such that it becomes two parts, right? X and Y, such that the edges between X and Y is minimized. So this part is called EXY. We have a graph. We make the vertices into two parts, X and Y. And then we just look at how many edges between X and Y. And somehow we want to cut the vertex, cut the graph such that the minimum number of edges is used. We don't want to cut a lot of edges because it's not making sense. We want to cut as fewer as possible. But meanwhile, we want to make the X and Y be balanced. So such that X and Y have the same size and the number of edges in between is minimized. So for example, well, I don't have a good example, but let's try this one. I guess this one is quite obvious that you have 8 vertices, so you want to pick 4 vertices on X and 4 vertices on Y, and so that X and Y there's as fewer edges in between as fewer as possible. So you can cut that into this part. So this is X and Y. So they are balanced, and also the number of edges in between X and Y is equal to 1. This is the minimum possible. It cannot be fewer. But it is not always easy. Let's see. Yeah, it is just not always easy. Okay. So we want to formulate this one into mathematical questions. All right, so how to formulate the problem? Suppose we have a partition, X and Y. Their union is equal to the whole vertex set, and they have no intersection. Okay, it is just a partition. We don't know whether it is balanced or not. And we don't know what is the edge set in between. Then we can say this phi of X and phi of Y, the characteristic vector of X and Y. So we have seen this before. It is a vector with a lot of zeros, but it has ones on the X, or it has ones on the Y. So we also make one particular vector, which is V. V vector is equal to phi x minus phi y. And in fact, it is phi y minus phi x. It also works. It doesn't really matter. We will see that in a few minutes. Just it's the difference between them. And in the other words, this V vector has a lot of ones on X, and it has a lot of minus ones on Y. It uses 1 and minus 1 to indicate which group it belongs to, whether it belongs to X or it belongs to Y. Now we have a few facts. V is orthogonal to 1 if and only if the partition is balanced. Right? Because V inner product with 1 is just equal to the sum of all entries on V. And on V, there are only 1 and minus 1. There are X copies of 1s and Y copies of minus 1. So if the sum is equal to 0, X should be equal to Y. The sizes are the same. So this is the first question, first condition. We want it to be balanced. And second observation is the following. If we do the quadratic form, it is equal to 4 times the size of xy. And the reason is the following. Because we know the quadratic form is equal to the summation of lots of edges, and we want to take the summation of vi minus vj squared. Okay, and somehow this vi minus vj squared is very easy to calculate. There is only a few possibilities. It can be 0 if ij belong to x or ij belong to y. Okay, if it both on the same side, then vi vj is both 1 or both minus 1. So their difference is equal to 0. However, if one side is in x, the other side is in y, then it is 2 squared, which is 4. It is 1 minus minus 1, and then take its square, which is 4. If, say, I in x, j in y. So in the end, it is basically counting how many numbers of 4s, and then counting I is adjacent to j, such that I in x, j in y. So in the end, you are just counting this quantity. So maybe let me move this to the second page. And take out this human. So suppose that we have the following equations, then we have the following observation. Q1 is, the original question, is equivalent to, we want to minimize VLV, because VLV is just 4 times the number of edges, and subject to V in Rn, of course, or maybe a bit better. V is a vector which is 1 or minus 1 in each entry, the Cartesian product of 1 and minus 1. Okay, and V is orthogonal to 1. So this part just means V is in Rn, and the entries is in 1 of 1 or minus 1. Okay. So our question was asking the minimum number of edges in between, and you want to run through all the different partitions. Now we switch the question into try to check the vector V. This vector V has all the entries in 1 or minus 1, indicating that each entry belongs to X or Y. And somehow you want this vector to be orthogonal to 1, so that the partition is balanced. The number of 1s equal to the number of minus 1s. And meanwhile, you want to minimize this quadratic form. And this quadratic form is the number of edges. So Q1 is equivalent to this one. And somehow, this is just hard. By hard, it means you have to run through all the different possibilities. There are lots of possibilities to partition the graph into two parts, and you have to check the minimum one. And the other way to say that this is integer programming. And integer programming is usually harder than the linear programming or other PSD programming. 就线性规划和整数规划，线性规划是简单很多的。Okay, so integer programming is harder. Although you can just use the brute force to find it, but integer programming is usually harder, way harder. Okay, so in contrast, we are going to change this question a little bit. Now let's change that to Q2. Q2 is try to relax the whole question a little bit. Again, it try to minimize V transpose V, V transpose LV. This is a quadratic form, but this time we want to restrict the vector V into different sets. We only want them to be a vector in Rn, but still it should be somehow balanced. The number of positive entries, the sum of positive entries is equal to the sum of the negative entries. The only difference is that previously it can only be 1 or minus 1, but now it can be any real number, but with the same condition. So this is the only difference. But now you see this is much easier. This is actually it is called positive definite programming, but you don't need to know the word at this point. Anyway, it is easier a lot because you know the answer. The answer is V transpose LV is going to be equal to what? Lambda 2 times the length of V squared. Okay, it depends on let's do one more condition. Sorry about this. And we also want V to have the length equal to 1. So this is an extra condition. But you know you can always scale the vector a little bit. So the answer to this optimization problem, it is much easier. The answer is just equal to lambda 2, and the V is equal to the eigenvector of lambda 2, the unit eigenvector of lambda 2. So you will see that V is equal to V1, V2, up to Vn, and this lambda 2 is an approximation to the question here, because these two problems are very similar, and this eigenvector is also an approximation to the partition. The previous partition is saying all the ones belong to one side and all the minus ones belong to the other side, and now we are going to say that okay, from these entries it belongs to positive side or it belongs to the negative sides. And here is what I meant. Let's say V has its entries called V1 to Vn, and we can define n plus. N plus of this vector, it is considering all the index of V of g such that Vi is greater than 0. And similarly, for all i's such that if vi is equal to 0, then we call that as v0. We can also define what is v minus. So what does that mean is like if you have a graph and you calculate lambda 2 and you calculate v, and v is equal to v1 up to v6. Okay, and these are some numbers. So you are going to label the numbers on these vertices. Maybe this is minus 0.2, minus 0.2, 0.2, 0.2, 0.1, minus 0.1. Okay, and then you will say, okay, these part are all the negative part. It is m minus, and these part are all the positive parts. It is m plus. So in conclusion, no matter you take m plus union with n0 and m minus, this is a partition of the whole graph, right? Or you can take m plus and then take the n0 to m minus. It doesn't really matter. It can be an approximation solution, approximated solution to Q1. Because Q1 is somehow, we don't have the answer, but Q1, like Q2 will provide a partial solution or approximated solution to Q1.